Section 14.7, triple integrals in other coordinates, specifically cylindrical and spherical. So remember, cylindrical was polar coordinates with a z, so cylindrical wasn't a bad deal. We had x equal to r cosine theta, y equal to r sine theta, z equal to z, r squared equal to x squared plus y squared, and tangent of theta equal to y over x. Okay. So let's take a look at the triple integral in cylindrical coordinates. If we have our triple integral over our solid region Q of the function f of x, y, z dv, okay, in cylindrical coordinates, that's going to be equal to our integral from theta 1 to theta 2 of our integral from g1 of theta to g2 of theta, okay, of, and this is the fun one, our integral of h1 of, so remember it was of xy, so we're replacing x and y now with its equivalent in polar coordinates, so that's r cosine theta, r sine theta, to h2 of r cosine theta, r sine theta, okay, of the function f of r cosine theta, r sine theta, z. And just like with polar coordinates, it's not just going to be dr d theta, it's r dr d theta. So we have to include that r, and then we have dz dr d theta. All right, let me shift this up a little bit here. Put a nice lovely box around it. Okay, so there is our triple integral in cylindrical coordinates. I keep saying polar, it's cylindrical because of the z component. All right, so let's do an example. Let's find the volume of a region. Find the volume of the region bounded by, okay, x squared plus y squared plus z squared is equal to r squared is equal to 4, and r equal to 2 sine of theta. All right, so the first thing I want you to notice is that the x squared plus y squared plus z squared is equal to 4. That's a sphere with radius 2. Okay. For r equal to 2 sine theta, we don't have a z component here. So this is going to be a cylinder. Cylinder that's going to run parallel to the z-axis. Okay. So I'm going to begin this by just kind of sketching the trace of r equal to 2 sine theta in the xy plane. So let's begin here. So I'll pick a few values for theta, plug them in. So I'll start with 0. Sine of 0 is 0, so that's going to be 0. Pi over 4, sine of pi over 4 is root 2 over 2. Multiply by 2, we get root 2. Pi over 2, sine of pi over 2 is 1, times 2 is 2. 3 pi over 4, it's going to be root 2 over 2 again, so that's going to be back to root 2. Pi, just pi, that's going to be 0 again. 5 pi over 4, it's going to take me to negative root 2. 3 pi over 2, it's going to be negative 1. Oh, negative 2. Negative 1 times 2 is negative 2. And then 7 pi over 4 is negative root 2 again, and then back to 0. So 2 pi. Okay, so this is going to make a bit of a loop here. So let's go ahead and sketch that, see what that looks like in the xy plane. So we begin with 0, 0, and then we have an angle of pi over 4. It goes out to root 2. So if this is 1 and this is 2, this is going to take us out here to root 2 at pi over 4. So that'll be about here-ish. Okay. Oh, my scale's atrocious. Let me try to fix that a little bit, just so that it looks a little bit better. 1, 2, there we go. Okay. There we go. And at pi over 2, we are up to 2. And then at 3 pi over 4, we're back to root 2. So about there-ish. And then we're back to 0. And then 5 pi over 4 puts us at negative root 2. So 5 pi over 4 is down here, but we go negative root 2 over 2 and it takes us back. So what this is doing is this is bringing us around and then taking us back around the same curve a second time. So really we can stop right here and say our theta is between 0 and pi for this curve. Alrighty, so that helps us out. That tells us what we need to know about that. And now we know what this looks like. Okay, now we're going to look at our sphere of radius 2. So let's go ahead and try to translate all of this into 3 dimensions. Okay, so we have x positive here, y positive here, z positive here. And this guy, this curve that we saw here, is kind of coming out like this and coming back here like this. So we're kind of getting this curve here, and it is a cylinder, so it is going to shoot straight up. All right, fix that, make that a little more vertical. There we go. So it's going to come just like this, okay? Now our sphere has radius 2, so it's going to intersect the y-axis at 2 as well. And it's going to intersect every axis at 2 here, actually, including the z-axis. All right, so here's our sphere. Okay, all right, so that's beautiful. Wow, I mean, I can't even imagine you not seeing what I'm actually trying to draw here. Let me try to draw it this way. So if I've got a sphere, and I cut that sphere down the middle, then right over here, we've got this kind of shape happening that's intersecting it here. And so it almost looks like, if you took the region, it almost looks like a little bit of a, maybe a taco shell. I don't know. Let me draw it for you, because that shape is cutting here and here. So it would follow along the sphere surface until it got to here and got to here, right? So there, it would be empty here. The cylinder would be empty here on the outside of the sphere. So what we're ending up with is something that looks a bit like this. So if I just looked at this straight from the y-axis, if I'm looking straight down the y-axis, this is where it's touching the y-axis, and then z is going up and down and x is going left and right here. This is kind of what it would look like. It would be kind of coming down from the sphere like this. And then we would be capturing kind of the maximum and the minimum of the sphere, and then the sides of the cylinder would give it. So that's what I meant when I said it kind of looks like a folded up taco shell, maybe, or maybe a scroll that was cut in a circle. If you rolled a circle and took a circle and kind of rolled it up like a scroll, it's kind of what you're seeing here. Okay, so that's lovely and very, very difficult to explain. When you cannot see my hands or any manipulatives I might have been able to show you. Okay, hopefully that's making some sense, but this is the region that we're dealing with. Now, we have got to figure out how to set up our boundaries for theta, r, and z. So z is not too bad, I don't think. Z is running from its lowest point on the sphere and its highest point on the sphere. So we're going to be able to use our equation of the sphere to obtain those values. Now, R we know begins at 0 and it's going out to whatever is given to us by its function value. R is 2 sine theta, right? So theta, we already figured out theta, it's going from 0 to pi. If we go around twice, we're duplicating ourselves, so we only want to go around the one time. Okay, so let's see if we can't set this up. Z is going to be between the lower part of our sphere and the upper part of our sphere. So the sphere was x squared plus y squared plus z squared equal to 4. So z is plus or minus the square root of x, 4 minus x squared minus y squared, right? There we go. So that's z. So our upper boundary is the square root of, you know what? Let me just put that over here where I've already started. Less than or equal to the positive square root of 4 minus x squared minus y squared, and the negative square root of 4 minus x squared minus y squared. Okay? But the problem is we're not doing this in rectangular coordinates. We need this to be in terms of r and theta. Well, that's pretty easy to do because we just have negative r squared sitting right here. So our z is between square root of 4 minus r squared and the negative square root of 4 minus r squared. So that's our boundary on z. Okay, so z runs vertically. How low does it go? To the bottom of the sphere. How high does it go? To the top of the sphere. All right, so there's that one. Now let's talk about r. Well, we already know r. R is given by 2 sine of theta. So that means r is going to be between 0 and 2 sine theta. Okay, so there's our boundary on r. And finally, we already found this, our boundaries on theta. Theta is just going to be between 0 and pi. And there we have it. So at this point, this is a very straightforward integral. Now we're just looking for the volume. So there's not any function that's going to be inside of the integral, right? We're just looking for our volume. So if you remember from the last section, 14.6, that volume is just the triple integral over dv. Okay, so dv here is going to be, well, let me just do this. So volume is the triple integral over the region Q of dv, you know, with respect to dv. So for us, that is going to be the integral for, well, it's a triple integral, and it's going to be dz, dr, d theta, but as with all polar coordinates, whenever we substitute in the dr d theta, it's not just dr d theta, we've got the r there as well. So dv in cylindrical coordinates is r dz dr d theta. So something to be aware of there. Let me actually jot that down. Dv is equal to r dz dr d theta in cylindrical coordinates, okay? All right, so let's go ahead and get all of this filled out, our integrals filled out. I'm going to erase them because I need some more space. For theta, we're just going from 0 to pi. That's pretty straightforward, just constant values, which is exactly what we needed. For r, we're going from 0 to 2 sine theta, right? And then for z, we are going to be running between the positive and the negative square root of 4 minus r squared. So negative square root of 4 minus r squared to positive square root of 4 minus r squared. And that's it. That's what we've got. So this is something that we can go ahead and integrate. Okay, so let's jump right into integrating this thing. All right, so this is going to be equal to the integral from 0 to pi of the integral from 0 to 2 sine of theta of our z evaluated from negative root 4 minus r squared to positive root 4 minus r squared dr d theta. All right, so pop those in. This is our integral from 0 to pi of our integral from 0 to 2 sine of theta of r times the square root of 4 minus r squared minus the negative square root of 4 minus r squared dr d theta. So distributing that, or simplifying it actually, is going to give us 0 to pi integral from 0 to 2 sine theta of 2r square root of 4 minus r squared. Subtracting a negative makes it a positive, dr d theta. So I'm going to go ahead and pull the, you know what? I'm not. So I was going to say I was going to pull the 2 out, but then it dawned on me that I'm going to do a u sub with 4 minus r squared, giving me u equal to 2r dr. And that's 2r dr. I can just do a substitution there. So that's the next step. Let's do a u sub. So let u equal to 4 minus r squared, then du is equal to negative 2r dr, so negative du is equal to 2r dr, and so we have our substitution right there. So let's do that. So this is our integral from 0 to pi of our integral from 0 to 2 sine theta. Well, I can change the boundaries, but with 4 minus r squared, oh, you know what, it wouldn't hurt anything. Let's go ahead and do it. So to change the boundaries for u, making these boundaries in u now, I've got u is 4 minus r squared. These are r values. Let me do another color. These are r values. So u is 4 minus r squared. 4 minus 0 squared is 4. So my lower boundary on u is going to be 4. My upper boundary on u is 4 minus 4 sine squared. So 4 minus 2 sine theta, quantity squared, is 4 sine squared. So 4 minus 4 sine squared of theta. There we go. That way I don't have to switch back to r later. Okay, and then my substitution, 2r dr is a negative du, and then that's the square root of u. So there we have it. We substituted 2r dr for negative du, so there's my negative in du, and then the square root of 4 minus r squared is the square root of u. So we can integrate that. So that's going to become negative 2/3 u to the 3/2 evaluated from 4 to 4 minus 4 sine squared theta d theta. I dropped my d theta above. Let's make sure we add that. So that's what's left there is the d theta. So this is our integral from 0 to pi of, okay, so putting all this down. Actually, I want to pull out the negative 2/3. Let's do that. Integral from 0 to pi. Okay, so this is going to be 4 minus 4 sine squared theta to the 3/2 minus 4 to the 3/2 d theta. 4 to the 3/2 is 3/8. I can factor the 4 out from here, and I'm left with 1 minus sine squared, so that's negative 2/3 integral 0 to pi. 4 to the 3/2 is 8 times 1 minus sine squared theta to the 3/2 minus 8 d theta. Factor out the 8 and change 1 minus sine squared to cosine squared. And this is negative 16/3 integral from 0 to pi of, okay, so let's see, that's going to be cosine squared to the 3/2 minus 1 d theta. Now cosine squared to the 3/2 is just cosine cubed. Theta minus 1 d theta. So that's negative 16 cubed integral from 0 to pi cosine cubed theta d theta minus negative 16/3 integral from 0 to pi of 1 d theta. Okay, so this first integral, the reason I've written it this way is I wanted to point out to you, for this first integral, we are going to run into a little bit of trouble, because if you recall, the graph of cosine of theta begins at 1, and at pi over 2 hits 0, and then at pi is back to negative 1. So the trouble with that is when we integrate from 0 to pi, it's going to zero itself out, because this area is equal to this area. The integral gives us this area as a positive and this area as a negative, and so it's going to zero itself out. So what we need to do, because we are looking for an area, is we need to notice that this is going to zero out. And to fix that, because we want a true area, we need to take half of it because it's symmetrical and then double it. So we're going to say this is going to be negative 16/3 times 2 times the integral from 0 to pi over 2 of cosine cubed of theta d theta plus 16/3. The integral from 0 to pi of d theta is just pi. So that's fundamental theorem of calculus at work for us there. All right, so now we have to deal with this integral here. So let's do that. So this is negative 32/3 times, oops, I went a little too far out with my parentheses, didn't I? Shouldn't have a parenthesis here. That parenthesis should be just here. Yes, okay. So 32/3 times our integral from 0 to pi over 2 of cosine cubed. So to do this, we're going to need to convert cosine squared to sine squared. So that's going to be 1 minus sine squared of theta times cosine of theta d theta. Okay, plus 16/3 pi. All right, so then now I can do a u substitution here without too much difficulty. So I'm going to let u be sine of theta, then du is cosine theta d theta, and then I've got a nice substitution there. So let's do that. So this is negative 32/3 times the integral from 0 to pi over 2, but that was when we were working with theta. Now I'm going to be working with u. So the sine of u is 0. The sine of pi over 2 is 1. I think I said sine of u, sorry. U is 0 if theta is 0, because u is sine of theta. So sine of 0 is 0, so you'll be 0 on the lower boundary. Sine of pi over 2 is 1, so you will be 1 on its upper boundary. And this becomes 1 minus u squared, and then cosine theta d theta is du plus 16/3 pi. All right, so let's integrate. So this is negative 32/3 times, okay, so u minus, add 1 and divide, that'll be 1/3 u cubed, evaluated from 0 to 1, plus 16/3 pi. So this is negative 32/3 times 1 minus 1/3 minus 0, u plugging in a 0 for u gives us a 0, plus 16/3 pi. So 1 minus 1/3 is going to be 2/3 plus 16/3 pi. All right, so this is going to come out to be negative 64/3 plus 16/3 pi. And this is a volume where we're looking for, so that had better be positive. So we need to put that into our calculator to make sure that that's positive, to make sure I haven't made a mistake somewhere. So I'm going to take negative 64/9. Oh, yeah, 3 times 3 is 9. I wrote down 3. Let me fix that. Hopefully you guys caught that. So that should be a 9 right there. There we go. Yes. So negative 64/9 plus 16 pi over 3 is going to give me 9.6. So this is greater than 0, so we are okay. That is our final answer. So that's the volume of this thing. So the tricky part of this particular example was recognizing that we were taking an integral of cosine from 0 to pi, where it would zero itself out, but we needed a real value. We needed to know what those actual numbers were. So we had to split it in half and then double it. So using the symmetry of cosine there across pi over 2. Okay, enough of that rambling. So that's the end of this example. Let's go on and talk about spherical coordinates. Okay. So the first thing I want to point out is, for very much the same reasons that we had to do r, dr, d theta, dv is not just going to be d rho, d phi, d theta, right, in spherical coordinates. Oh, we should probably recap our spherical coordinates real quick. All right, so just to recall, we've got x is equal to rho sine of phi cosine of theta, y is equal to rho sine phi sine of theta, and z is equal to rho cosine of phi. Dx dy, this is what I was getting at, dx dy dv is not just going to be just rho d theta, or d rho d phi d theta. It's going to be more than that. So let's go ahead and make note of this. So dv, which was dz dy dx, right, in rectangular coordinates, is going to be equal to rho squared sine of phi d rho d phi d theta. D rho d phi d theta. d phi. Oh, no, I'm sorry. It's been a very long day of recording. Okay, so this is something very important. So this is something to keep in mind. We do have to be conscious of this. So this is like adding r to the dz dr d theta. This, though, we have to add phi, rho squared sine of phi. So just to be aware of that, we have that there. All right, so let's go ahead and write down the triple integral here. So I've got my triple integral over q of f of x, y, z dv. Okay, that's going to be equal to, so I need a lot of space for this one, so just warning. It's going to be equal to our integral from theta 1 to theta 2 of our integral from phi 1 to phi 2 of our integral of rho 1 to rho 2 of f of, okay, here we go, rho sine phi cosine theta. Okay, so just x in spherical coordinates, y in spherical, which is rho sine phi sine theta, and then the z is rho cosine phi. All right, times rho squared sine phi, so that's that little extra bit we have to include for the dv. Then integrate with respect to rho, phi, and theta. Okay. So let's go ahead and do an example using that. So set up the triple integral in spherical coordinates, and we have a region bounded by z squared equal to x squared plus y squared, and x squared plus y squared plus z squared equal to 9. So we're going to use a triple integral to evaluate. Actually, you know what I'd like to do for this one? Let's not use a triple integral to evaluate it, because part of your homework is going to ask you just to set up the integrals and not actually work them. So let's just set up the triple integral. Set up the triple integral to determine the volume of the region bounded by, okay, this, do not evaluate. You'll be very angry if you're doing your homework and you go through all this work to evaluate a triple integral and it turns out all it wanted from you was the actual integral itself. So just be aware of that while you're doing your homework. I think there are 2 of those in this section. Anyway, let's go ahead and set this up. So what are we dealing with? This is a sphere of radius 3. This is a cone. It's a regular right cone. So if I were to draw my sphere, okay, the cone is going to begin here at the origin, and it's going to be just, let's see, straight up like this. Okay. All right, so there's our region. It's kind of like a snow cone. Okay, so we've got to set this up. Now, because we have got z squared equal to x squared plus y squared, what we know is that the angle phi is not too difficult to find because, I mean, think about it. If we put this into the zx trace or the xz trace, I guess I should say, or the yz trace, we're going to be able to find that angle pretty simply. So let's take a look here. If I've got this z squared equal to x squared, then my phi, my angle right here, is just pi over 4. Right, because it's equal to that. And as we are moving around that circle, that angle is going to remain constant because this is creating a circle, and that's true at any point along the cone. So because of that, that angle formed there is going to be constant, and we have our phi is equal to pi over 4. Okay, so that, remember, that's the angle made with the positive z-axis, that's phi. Okay, so now theta. This guy's going all the way around, right? So theta is clearly going to be 0 to 2 pi. So theta is going to be going, I guess it would be from over here, but theta is going to be all the way around. So we've got phi equal to pi over 4, and we've got theta equal to, well, between 0 and 2 pi. Okay, and then we need to figure out what is rho. So remember, rho is the distance from the origin to the point. So rho could be a different color. Let me get another color. Wow. I'm trying. All right, rho. So rho is just this distance. Well, the cool thing about that is this distance is actually constant because we are in a sphere of radius 3. So rho is just equal to 3. So my distance will be going from 0 up to 3. So this one's lovely. It's really quite straightforward to set up. Let's go ahead and do that. So this is our integral for phi. For theta, we're going from 0 to 2 pi. Then phi, we are going from 0 to pi over 4. Then for phi, for rho, we are going from 0 to 3. And that's it. And then we have our dv. So that's rho squared sine of phi, d rho, d phi, d theta. And there it is. And this one actually would not be ridiculously difficult to evaluate if you wanted to do that. All right, folks, I'm going to end this one here. If you have any questions, as always, please let me know.